Our next unit is on equilibrium. So let's take a look at in general what equilibrium means and all kinds of other stuff. First of all, virtually all chemical reactions, all chemical processes are reversible. Not all of them, but many are. In order for a system to achieve equilibrium, a couple conditions must be met. First of all, the system must be in a closed container, and this isn't necessarily always the case, but better said that in order for a system to achieve and maintain equilibrium, it needs to be a closed system. So not necessarily a closed container. Let me explain the difference. A closed system means that no matter can enter or leave that system. So of course, if you have any gases involved in the reaction, then it must be a closed container so that those gases cannot leave. But if the reaction occurs in solution, as long as nothing is getting into or out of the solution, then technically that is a closed system. The other condition is that a constant temperature must be maintained in order to maintain equilibrium. We're going to look at systems at equilibrium from two different perspectives. One, the macroscopic view or macroscopic level, meaning what you can see with your eyes. And then the other is the particulates or submicroscopic level. So we're talking about what's happening with the individual particles that are involved with the reaction. So macroscopically, a system is at equilibrium, or we can tell that a system is at equilibrium if no further changes are observed. So it looks like nothing is happening. When we have, well, we'll get to it in a little bit. I don't want to get ahead of myself. Particulate level, a system is at equilibrium when the rates of the forward and reverse reactions are equal. Now, sometimes we get into a situation where either the forward or reverse reaction is faster for some particular reason. We'll talk about that when we get into Le Chatelier. So let's take a look at how we show that. This first, I got to go back up to number 2. Let's write a generic equation showing that the rates of the forward and reverse reactions are equal. So start off with the reactants. Always go on the left side. And then we use this two-way arrow, if you recall. And we have the products on the right side. As read from left to right, this is the forward reaction. And read from right to left, this is not the backwards, but rather the reverse reaction. And so what I'm going to do is I'm going to use the length of these arrows to represent the relative rates. So notice that the length of those two arrows are the same. That tells us that the rate of the forward and the rate of the reverse reaction are equal. So thinking ahead to Le Chatelier's principle, where you can apply a stress to a system at equilibrium, causing either the forward reaction to speed up or the reverse reaction to speed up. How do we show that? So if the forward reaction is faster for some reason than the reverse reaction, we can show it like that. Actually, I don't like to do it that way. Let's go. Actually, yeah, that's fine. So this tells us that the forward is faster than the reverse. Or actually here, I don't know which way I want to write it today. Let's go this way. That's fine. Either way, so we have a different length arrow. One left to right is longer than right to left, so forward reaction is faster. What if the reverse reaction is faster? How do we show that? Maybe something like that. So notice I use one-headed arrows. I don't use, double-headed arrows like that. So boom, boom, just like that. Let's do this. Let's show graphically what happens at equilibrium. In fact, I'm going to draw two different graphs in this space. So start the first one way over to the side. Let me set up my axes. So let's make a graph of amounts versus time. So that amount could be whatever, mass, it could be absorbance, it could be concentration. Usually we, draw graphs of concentration of the substances involved in a reaction versus time, or like we saw in the last lab, absorbance versus time here. So either way is fine. So let's start with this. Let's start off with the reactants. I'm going to represent them in blue. So as we saw in our last experiments, initially the concentration of the reactants are high, and the concentrations of those substances will decrease, not linearly, but decrease over the course of the reaction. Let's show in green what happens to the amount of the products during the chemical reaction. So at the very beginning, there are no products. And as the reaction proceeds, the concentrations of the products, as we see here, increase. So how about right about this time here? What do you notice happens to these substances? So at this point in time, the amounts of the reactants stop decreasing and the amounts of the products stop increasing. We would say then the system has reached equilibrium. So notice equilibrium does not mean equal amounts. Macroscopically, we have no further changes. So products stop forming, reactants stop being consumed, or so it appears. And so we say the system is at equilibrium. Let's draw another graph. Again, amounts versus time. And again, we'll use our same colors. So let's say we got our reactants here, concentrations decrease. And then we got our products, concentrations increase. And I don't know, right about there, I guess. After that long during the reaction, we see once again that's the reactants amounts stop decreasing, the products amounts stop increasing. Now, what's different about these graphs? At equilibrium, what is true about the amounts of the reactants compared to the amounts of the products? Well, we see in the first graph that at equilibrium, there are more reactants at equilibrium than there are products. This is significant. On the second graph, we see the opposite. At equilibrium, there are more products than there are reactants. Again, we'll talk about the significance of this later. Letter B there, equilibrium is achieved when no further changes are observed in the amounts of the chemicals. All right, particulate level, submicroscopic. Again, let's draw one graph this time. Let me set up my axes. So this time on the y-axis, we're going to put reaction rates. X-axis is going to be time, and again, I'm going to use couple different colors. So let's start off with this forward reaction. You take some reactants, put them in a container, allow them to react. Of course, we know that's during a reaction, the rate decreases. We talked about this with kinetics. As the concentrations of the reactants decrease, the rate of the reaction decreases. Again, notice not linearly. Reaction rate does not decrease linearly with time, but nevertheless it does decrease. And again, let's show in a different color. I don't know, I guess we'll use the same colors, but I want to make sure you understand that these are totally different graphs here. Green is our reverse reaction. So at the very beginning, we have no products. So there is no really rate of the reverse reaction at the beginning. It's not until we form products from the forward reaction that the reverse reaction then increases in rates. And we get something like that. So right here, what's going on? What do you notice? We have equal rates. We say the system has reached equilibrium. So be careful. Equilibrium does not mean equal amounts. Equilibrium means equal rates. All right, next up, let's take a look at what is called the equilibrium constant. So let's start off with the generic equation. So something simple. So let's do this. Let's write the rate laws for the forward reaction and for the reverse reaction. So let's start with the forward reaction. So the rate law is Kf, or the rate equals Kf times concentration of A squared times concentration of B. How about the rate law for the reverse reaction? So now remember, the rates at equilibrium are equal. So let's set the rate laws equal to each other. So Kf is the rate constant for the forward reaction. Kr is the rate constant for the reverse reaction. And so we get this. Now let's go ahead and rearrange this. Let's divide both sides by Kr. Let's also divide both sides by concentration of A squared B. So we get Kr cancels over there. A squared over B cancels there. So we get Kf over Kr equals concentration of A2B over concentration of A squared times B. Well, these are numbers, right? So the ratio of Kf to Kr is also a number that we call big K, capital K, the equilibrium constant. So big K equals concentration of A2B over concentration of A squared times concentration of B. So this is our equilibrium constant expression, it is known as. So let's take a look at what it says next. For a system at equilibrium, the ratio of the product of the concentration of the products over the product of the concentration of the reactants is always constant if temperature is held constant. A little note, if gases are part of the equilibrium system, then pressures may be used instead of concentrations. So there's all kinds of different Ks. Generically, we write KEQ for the symbol for the equilibrium constant, but we have all kinds of different Ks. If what we're dealing with are concentrations of substances, like here, we can write it as Kc. If we're dealing with pressures, we can write Kp. There's all kinds of different equilibrium constants besides Kc and Kp. We have Ka. Any guesses what the A stands for? That stands for acid. Kb, any guesses what the B stands for? That's base. Kw, W stands for water. KSP, the SP stands for solubility product. So these are all equilibrium constants. They all have some value. That value is constant at a particular temperature. Going back here, keep in mind that though, A and B are reactants and they're also products, to make things easier, we have to take an equation as written. Whatever's on the right side, we call the products, and whatever's on the left side, we call the reactants. So yes, true, A2B is also the reactant of the reverse reaction, but that gets really confusing. So when you set up an equilibrium expression, it's always concentration of the products on top, whatever's on the right side, over concentration of the reactants, whatever's on the left side. So let's take a little deeper look at this. So let's look at this equation here. Capital letters are the symbols of the chemicals, lowercase letters are the coefficients. So technically, we set it up this way. It's the concentrations of the products, each raised to their coefficient. It's kind of hard to see with the C there. Over concentrations of the reactants, each raised to their coefficients. So that is our equilibrium expression for this generic equation. Some important features, we already talked about it. Equilibrium constant is only constant at a certain temperature, meaning if you change the temperature of that system, then the equilibrium constant will also change. And when we're dealing with equilibrium expressions, even though we're plugging in concentrations, we're not going to use units. We're not going to plug in the units for each of the concentrations. We're just going to plug in numbers. And so the equilibrium constant K is unitless. There's a section in your book talks about why we do not include units. Has to do with actually these things called activities. Again, you can read more about that if you want, but just know K is unitless. Now be careful. The concentrations of solids and liquids technically is fixed. And as a result, they are not written in the equilibrium expression. So think of it this way, the concentrations of solids and liquids are already included in the value of K, and so we don't need to add them to our equilibrium expression. Likewise, concentration of water, or like I said, any other liquid in most aqueous solutions is virtually unchanged. Consequently, concentration of water or any other liquid is also omitted from the equilibrium expression. For example, let's say substance D was a solid and everything else was gases. What we would do is we would get rid of D. We could substitute for it a number 1. We don't have to put that number 1 here, but you could. Likewise, if A or B was a solid or liquid, we get rid of it and put a 1 there if we wanted. The only significance of that 1 is if both of your products are solids or liquids, and we have to put the 1 on top. All right, so here's what I was talking about before, the significance of the size of the equilibrium constant. So what does it mean if, let's say, K is greater than 1? Think about how we set that up. Products over reactants. If the value of K is greater than 1, that means there are more products at equilibrium than reactants. Or we say that the reaction is products favored. That's what products favored means. More products than reactants, like on our graph. Let's take a look. So we'll call it graph number 2. According to graph number 2, there are more products at equilibrium than there are reactants. So if this is the case, then the value of K would be greater than 1. Conversely, if K is less than 1, so you got a decimal number, 0.0, point something, then that means the top is smaller than the bottom. Less products than reactants, or more reactants than products. That means the reactants are favored. And so that would be like graph number 1, where at equilibrium, the concentrations of the reactants are greater than the products. Now I know this is really confusing. How can you have different amounts of reactants and products at equilibrium? This will definitely make more sense when we talk about solutions of weak acids next unit. Now, though it's not always possible, but it does happen. If K is equal to 1, then of course that means the amounts of the reactants and products are about the same. All right, I think we'll stop there for now. Our next lesson, we will do calculations involving the equilibrium constant. All right, thanks for watching.